Welcome back to the channel, everyone. For today, we will be discussing NumPy, or other people would like to call it or pronounce it as NumPy, but seeing that it's numerical Python for this course, we will call it NumPy. Now, NumPy is at the forefront of a lot of efficient numerical computations, and if you aspire to be a data analyst or data scientist at one point in time, you will have to utilize NumPy. We will be tackling about the most important techniques, methods, functions that you need to learn and master in order for you to work well with NumPy. So if you go and visit the website dedicated to NumPy, you'll see one interesting case study. Back in 2019, the Event Horizon Telescope captured an image of the black hole at the center of the M87 galaxy, a task that many thought actually would be impossible at the time. Now, this image, a stunning visual confirmation of Einstein's theory of general relativity, was made possible by an international collaboration of over 200 scientists. At the heart of this achievement was the NumPy library, which of course allowed researchers to handle and process massive astronomical data sets efficiently. And that is what we want you to take away from using NumPy. NumPy is really efficient in terms of handling computation, especially when it involves large data sets of numbers. So the efficiency for numerical computation is really the key strength of NumPy. NumPy stands for Numerical Python. It's an open source framework that provides support for multidimensional arrays and matrices. Now you might wonder, why do we need to have NumPy when we can operate on lists? Well, the simple answer is that it's much more easier to perform calculations on NumPy arrays. Because NumPy arrays are homogeneous, meaning that all its arrays have elements of the same data type, it's much more easier to perform calculations due to the fact that these are memory efficient. So statistical functions, mathematical functions are easily carried out through this. NumPy doesn't always come pre-installed with Python, so if you need to install it and you found out that it isn't installed in your system, my packages video in this channel would be able to show you how to install NumPy. So let's first make sure you have NumPy installed. So if you don't, you can easily just install it. So using this command, we can check if it's installed. If it outputs requirement already satisfied, then the next thing to do is import NumPy, and our shorthand would be NP. Okay. If you want to know the version, it's np dot, because you've imported it as, or you use the shorthand np dot __ version. Okay. So for this tutorial, we're using 1.23.5. Now, in this case, let's create our first array. To create our first array, we simply do the following. Let's call it array 1D, and it's np dot array, and we have here, let's say 5, 6, 9, 10, 15. Okay, arrays are the heart of NumPy. Arrays are like lists but optimized for numerical data, so you'll see why computations are so much easier with this one. And if we want to view it, okay, similar to the other tutorials, you could apply some of our basic functions. So for example, for the len, you could see the length of array 1D, it's 5. Okay, but another interesting application or method that you can call on arrays is the shape. Okay, so that shape. Now you see here, whenever you're faced with, or whenever the number returned is of this format, it means that it's a one-dimensional array. If you want to be technical, it's a vector with 5 elements. Okay, so 5 comma means nothing is coming after that. It's just a one-dimensional array or a vector. So to to access it or to index it. For example, you want to get the first element, you do this. If you want to get the last element, it's the same. If you want to index it or slice it, rather, you could do this too. And basically the same operations that we've been doing with the lists, but you have the dot shape. Now, one of the best things about NumPy is how easy it is to make mathematical operations. Instead of writing loops, you can perform element-wise operations directly on arrays. So for example, for this one, I could do +5. And if I want to see what the output is, you have this. So each element of the array 1D has been added with the value 5. Or 5 has been added to those elements. If I want to subtract it, we have this. And of course, if you want to see multiplication, it's really just this. You can see operations like addition, subtraction, and multiplication are applied to each element automatically. This has a very specific term. It's called broadcasting. It's NumPy's way of handling operations between arrays of different shapes. Broadcasting allows smaller arrays to be automatically stretched to match the size of larger arrays when performing the operations. So, of course, this feature makes NumPy super powerful for handling large datasets efficiently. Pause and think about it. How would you do this for a list? You'd probably do a loop. Now, what if you need to change the shape of your array? NumPy makes that easy with the reshape function. You've seen earlier the dot shape function, and suppose, for example, you want to reshape, so let's call it a reshape array, your array 1D. Okay, we want to call on the reshape function here, or rather np.reshape. The first positional argument will be that of one of your array that you need to reshape, and the second positional argument would be the shape that you want it to be. So here, if you see the reshaped array, you basically reshaped it to be of 2-dimension, right? 2-dimension because you have two numbers here. Remember earlier, the 1-dimensional array has this shape, but a 2-dimensional array has this shape. Now, to call on the dot shape function here, you see that you now have the exact shape that you want, which is 1, 5, meaning that it's now a 2-dimensional array with 1 row and 5 columns or 5 elements. So for this basic function, let's wrap up with array concatenation and splitting. If you have two NumPy arrays, NumPy makes it easy to join them together or split them apart. So let's say, for example, let's create two array A here. And it's, take note of the syntax. If you're creating an array, an input here would be of list form. Entry. And let's make array B So to concatenate it, let's store it with the variable concatenated array. Simply call on but on the concatenate function, instead of a list, you have a tuple. Right? The tuple of the arrays that you'd like to concatenate. And to view that, there you have it. It's just one array. To split this array that we have concatenated, we can, let's try it on another one. The first one that we have made. To split the array, split arrays here, for example, we wanna split array 1D with, let's say, 2. Okay, so for np.split, the first argument is the array that you'd want to split on, and the second argument would simply be the index to split, where you want the split to start happening. Okay, but if you have the integer here, it will divide it into two equal array, but because it's not even, 2 won't work. But if you have 5, then split arrays would give you 5 different arrays. Okay, but if you input it with, let's say, this format, this will be read as an index, so it would start to split on that index. Okay, randomness is critical in many fields, whether you're simulating outcomes, generating synthetic data, or running probability experiments. By the end of this module, you'll learn how to generate random numbers, set seed for reproducibility, and sample from the different probability distributions. Let's start. Let's start simple. To generate random numbers in NumPy, we use np.random.random. This allows us to generate numbers between 0 and 1 by default. So, for example, np.random.random, okay? So you'll have here a number that is between 0 and 1. It's important to note that every time we run this, as you see, the number will change. But randomness isn't always random, especially when we want to have some reproducibility. So in data science and research, reproducibility is key. If you're working on a project and need to get the same results every time you run your code, you'll want to set a seed for your random number generator. So let's say, for example, for my students, they want me, for example, to check their output, and I need to confirm that they really did get that number. You need to have a seed. Or for other publications, or maybe in corporate, you want to ensure that the random process that you have observed will still be there when you present it to your boss, then you need to have a seed. So to put a seed so that we ensure that the same number gets reproduced the same time, we use here, so seeding random.seed. Okay, so in here, you'll have to input any integer. So let's say, for example, let's have 89. So now, once I run np.random.random and I run this again, it will still be the same number. Notice if I change the random.seed to a different number, say 95, now this code np.random.random runs, but it will produce a different number. However, because I haven't changed this, it's still 95. If I run this again, it will still be 0.22. If I run this again, but on a different cell, it would produce a different number because the seed works only in the cell. So this is a very key part of structuring your code. Where there is the random number, or where you're generating the random number, if you want to set a seed for reproducibility, that is where this particular code should be. Okay, you can try different numbers, you can even try a very long one, and you'll have something that is reproducible. One strategy to deal with this one is to store it in a variable that we can call random state. So for example, let's store it in a random state variable, and let's just call the np.random.random state. Note that the R and the S are both capitalized, and here is where you can likewise again input your integer. So let's say, for example, 0. And now when you generate your random number, you could call in, let's say, from a uniform distribution, or in the normal, or the binomial, or the Poisson, which I will discuss separately. One interesting aspect of generating random numbers is you generating it from a particular distribution. So there are other functions or other distributions where you could get your random number from. It's just that the np.random.random, which runs from 0 to 1, is really very helpful, let's say, when you are dealing with something that naturally is included or just naturally has a bound of 0 and 1. Let's say percentage, let's say proportion of let's say asset classes. So random np.random.random is a good distribution to generate random number from. But let's say, for example, you're rolling a 6-sided die and you want to simulate rolling it multiple times. So how do you do this in NumPy? So in that case, let's do that now. Dice rolls. So here, it's from the rand int distribution, meaning you want your drawn number or random number to be integer, and you can utilize the size parameter. So let's say, for example, you want to have a sample of 10 rolls. So in this case, you could check what your rolls are. So in this sampling, you're able to roll 10 times, where you roll the 6, a 2, a 3, a 2, a 4, a 4, a 3, 6, 4, 4. Okay, so using np.random.rand int, okay, we can simulate rolling a die 10 times where each roll is a random number between 1 and 6. This is how NumPy is useful in simulating real-life experiments. Now let's dive deeper into sampling from specific distributions. One of the most common distribution you'll encounter is the uniform distribution, where every value in a given range has an equal probability of occurring. And to generate from that distribution, it's np.random.uniform. The endpoints would be 0 and 10 for our case, and let's say the size is equal to 5. So to view that, we have this. Because the uniform distribution isn't a random integer distribution, or it's not rand int, even the decimal in between will be part of the distribution. So everything from these endpoints have an equal chance of being drawn. Okay, so you could increase that and you have more. Okay, again, this is good for those type of instances where it's natural to have decimal value in between once you've drawn that number. But if only integers make sense, then you will draw it from the np.random.random. Now let's explore the binomial distribution. This is often used to model binary outcomes like flipping a coin or checking if someone voted in an election. So let's say, for example, imagine we're flipping a coin 10 times. How often will it land heads, or how often will it be tails? So let's have it here. Oops. So it's from the, you guess it, binomial. Just change this one and let the n be 1, and the p is the probability of getting a positive outcome. So there needs to be a little bit of review here, but if the probability of getting a heads or a tails is just equal, p is always going to be 0.5, and let the size be equal to 10. Okay, so if you print coin flips, you see that per flip and 10 occurrence, you get heads, tails, tails, head, head, head. And as with our first random number, if you don't put a seed here, it will change. Okay, so if you want it to be reproducible, you would again put here np.random.seed. Okay, let's say for example 10, And now it will still be the same. However, remember earlier I told you to create a random state. Now you can use that random state and just get this portion, the binomial, okay, and sorry, it's supposed to be random, not this one, it's random state. Okay, so basically you will replace these portions here, the np.random. So even here, if you want to get it from the uniform, the np.random will be replaced by random state. Okay, and okay, sorry, and that would be a very good way for you to always have this variable where you can attach your simulations and it already has a seed value in it. Of course, with this binomial distribution, you can model any kind of yes or no event, whether you're flipping a coin, testing for a disease, or maybe even modeling customer purchases or even customer churn. Another important distribution is the normal or the Gaussian distribution. This is the famous bell curve where most values cluster around the mean. So to generate samples from the normal distribution, let's just call this normal dist. Call on the np.random.normal, and the default values is that the mean is 0 and the standard deviation is 1, and let's say you want a size of 5, but we will change that later so that you can use it to sample from another type of data that you have in mind, provided you know, of course, their mean and standard deviation. So the formula, or rather the parameter for that one, is can be found here. So np.random.normal. So the location here is, of course, the center of the distribution. That's the location, and the scale parameters, that's standard deviation. So suppose, for example, I want to simulate the scores of students, and from experience, scores of students can be normally distributed. That's why you have the bell curve where professors would curve the grade, right? So let's say, for example, the mean of the grade is 78 and the standard deviation is let's say 5. So if I want to simulate what they would get, for example, for different students, and let's say, for example, I have 20 students, then this would be the grades that they would be getting. Next up, we have the Poisson distribution, which is often used to model rare events. Imagine you're running a website and want to model the number of people who visit in a minute. On average, you may get 5 visitors per minute. So let's use the Poisson distribution to simulate how many visitors might come in a given minute. So for the Poisson distribution, let's model it. Here we generate 10 samples from the Poisson distribution with a mean of 5. This shows us how many visitors we might expect to come each minute, where some minutes might have more or fewer than average. So maybe in the first minute I have 6, in the second minute I have 2, and the third minute I have 7. So the Poisson distribution can help you simulate this. In analyzing whether you have enough samples from, let's say, your random distribution, it's often a good practice to visualize it. If you haven't watched my video on Matplotlib, please do so, because a lot of the things that I will be using will be directly lifted off from that. So, okay, combining what we know from the Matplotlib video and what you've just learned about the random number generation, then let's first generate random samples. Let's have a size parameter variable different from for each of the runs, so that we'll just want to see how our visualization or our distribution change with the number of size. So first, of course, we have to import matplotlib. And of course, okay, and we use the np that random state, so we can control the random process or the random number generation. See how I would maybe choose 19 right now, and then let's generate random samples from different distributions. Let's have a size value here. Maybe, for example, let's start with 10, and let's generate samples from the different distributions. Uniform, the uniform one, random state that uniform, so from 0 to 1, or maybe from 0 to 10, and let the size be equal to the size. Normal. And the size, okay. So n will be equal to 1. We haven't discussed why this is 1. This is the number of experiments per run. So you just really want one run per experiment with the probability of success being equal to 0.5. If you, let's say, for example, make this 2, 3, or 4, it will return to you the average of those, for example, 5 experiments. So you would expect that the average of those 5 experiments to be around 2.5 or something. But since we just want one, for example, one toss of a coin or one instance of that experiment, n will be equal to 1. In most cases, you can control anyway how many times you've run that, or for example, if you need more than one sample with a size parameter. And of course, the Poisson distribution. And we really just need the mean there. It's the positional argument. And so here, the mean of the Poisson distribution is 5. Now we go to the matplotlib proper, where first I will create a figure that would contain all of these 4 plots. We have 4 plots, so plt.figure. Fig size would be at 12 by 8. Okay. And we have here the uniform distribution. So I'll explain what this is for now. Let's take it as this, 2, 2, 1. And we want a histogram where we want the uniform D. The bins will be 30. Let the color be blue, and the alpha is equal to 0.7. The title be state, and let's label the value. So for the normal distribution, okay, so please pay attention to how we would change our graphs. So So basically, we can just copy this one, and it's 2, 2, 2. And then, of course, here you want the normal distribution. For the bins, it should still be okay to be 30, and let this be green. The alpha 0.7 is okay, but this is, of course, the normal distribution with a mean of 0 and STD, or standard deviation, of 1. Okay, so okay. Random state, X label will be value, and of course the Y label will be the frequency. Okay. In fact, I think we can also just put here frequency. Okay, so because it's a histogram, it's supposed to be the frequency anyway. For the binomial distribution, we could okay, change this to binomial. So it will be 2, 2, 2, and then 3. And of course, here you have the binomial. But because you only have 2 outcomes, your bins should just be 2. And let the color be red. And of course, we go with the binomial distribution with a p equals to 0.5, 50% chance of success. And last but not the least, we'll copy this for the Poisson distribution. And you have here 4. And the bins here, you can make not 2 but maybe 20, and then let the color be purple. And we can just say here equals to 5. Okay, and now should adjust the layout. If you have more than one plot in your figure, it will be good to have this PLT, that tight layout, so that it's of course it would present a tight layout. That's what it is. And because we have matplotlib inline, we don't need PLT show. Okay, so to generate that, hopefully there's no error. Okay, so there's an error here. What's the error? The error is figure set. Okay, it's supposed to be fig size or figure size. Did you catch that? Okay, so here's what the PLT.subplot meant. So you create a figure, so it's your canvas, and you want to divide your canvas into four plots, right? So basically what this is saying is that create in a subplot where there are 2 rows and 2 columns. Basically this is it, 2 rows and 2 columns. This plot will occupy the first one. The numbering goes 1, 2, 3, 4. Okay, so if you ever divide that by 6, it's 1, 2, 3, 4, 5, 6. So it's always from left to right, and then once you've exhausted it, the next numbering would be of course the next row. So it's always row-wise numbering. So 1, 2, 3, 4. That's why you have the normal distribution in 2, 2, 2. You have the binomial distribution in 2, 2, 3, right? And then the Poisson distribution for 2, 2, 4. Or a subplot with 2 rows and 2 columns and in the 4th position. Okay, so basically if you just have 10 size, right? So I think here the size is 10. You will have something like this one. So for example, for the Poisson, it's for the normal distribution, you have 2 counts here, 2, 4, 6, and then the rest would be just 1 instance. So if you try to increase it to 100, it's a little bit better. You're seeing the distribution that almost resembles the population distribution, right? The distribution that is found in the population. And what is it? Of course, you know that already. For example, for the normal distributions, it's with the mean of 0 and standard deviation of 1. So like it's very strongly, the points are clustered here, but you see that yes, there's some semblance of that now. If you increase that to 1000, then the convergence, the population is actually much stronger, of course, and you're free to increase it even more. And that's why with NumPy, the sampling for statistical purpose or for research purpose is actually something that is easier done. So hopefully this random sampling with NumPy and Matplotlib as a combination is quite helpful for you. You're doing your research and of course visualizing whether you have enough samples to approximate the population distribution. NumPy is actually really good as well with the statistical functions. Let's try to get the descriptive statistics. Of course, they help us understand the central tendency and the spread of the data. So it's our mean, median, mode, standard deviation. It's very straightforward. So let's have a data. Let's say, for example, that data be NP array. Okay, so that's pretty straightforward. Next, we want to calculate the variance and the standard deviation. So for the variance, it's really just np that var of the data. Okay, and standard deviation, of course, would be STD. Oops, sorry, error here. Sorry, data. Okay. Now we go on to other advanced statistics. For others, this would be advanced, but for some of you who's probably dealing with this regularly, say for example you're a risk or finance or portfolio manager, covariance and correlation is probably pretty ordinary already. But covariance and correlation help us understand the relationship between two data sets. Of course, covariance measures how the two variables change together, while the correlation tells us how strong the relationship is. So let's say, for example, we need to have two data sets here. Let's have the height and the weight. So let's say, for example, height. Okay, and here we have the weight. Just keep it simple for now. Okay, let's calculate the covariance matrix. Alright, so the covariance matrix shows us that the height and the weight change together. So as you could see here, it's positive. There's literature that tells us how to interpret this exactly, but just a quick FYI for the covariance, the magnitude is actually a little bit difficult to understand, so we mainly just look at the sign for the covariance. And of course here, the correlation coefficient is 1. Every 10 increase here, another 10 increase here. So you would expect that it's 1. It runs from -1 to 1. But let's say, for example, we make this so that every 10 increase here, this one decreases. So let's make this 40, 30, 20, and then 10. Okay, so now the covariance matrix is showing a negative sign, and of course here you have a -1 correlation coefficient. Let's talk about percentiles and quantiles, which are useful for understanding the distribution of data. Percentiles show the value below which a given percentage of observations fall. For example, the 90th percentile means that 90% of the data falls below that value. So let's say, for example, we have here percentiles. So let's calculate the 25th, 50th, which is the 50th, by the way, is also the median, okay? And 75th percentiles, okay? So, for the data percentile, for the first argument here will be the NumPy array, and that's the data. And here is the 25th, 50th, and then 75th percentile. So let's print the okay, so if you look at the data that we have here, okay, it really is saying that 25% of the data falls below the value of 28. The median is 45, meaning 50% of the data is automatically equal or less than 45. So we can take a look at that. So for example, here we have 1, 2, 3, 4, 5, 6, 7, 8. So 25th percentile means that two values below that, here it calculated that it's 28. 25% of that value falls below that, and you can see that that's true because here 15 and 25 falls below that. For 45, that would be the median. We've likewise computed that value here, and for this one, 3/4 of the data falls below 65.75, so it means that only two values are higher than that, and that's basically correct. We have 68 and 72. Now let's apply what we've learned to a real-life example. So let's say, imagine you're working for a company that tracks monthly sales data, and you want to calculate the average sales, the median sales, and see how consistent they are throughout the year. So let's say, for example, you're given the monthly sales data in millions, for example. And you have your sales. Okay. So let's just verify. So it's 11. So let's say, for example, let's have another one here. Okay, so 12 months. Okay, and we want to calculate Okay, the mean sales is around 210, and you can immediately interpret that, okay, there are certain months below that, and we need to understand why. The median sales is 205, so barring any outliers, which is really robust, and the standard deviation of sales is 56. Of course, for consistency, we want this to be lower because a higher number for standard deviation means it's more volatile. Okay, so and let's say, for example, we want to extend this further, and we want to analyze, for example, the correlation between marketing. So we want to, for example, have another data here, marketing spend, and see if they are at all correlated. So let's see, for example, okay. Okay, so okay, so let's say, for example, we have this, and we want to calculate, of course, the correlation coefficient to see if they are, of course, correlated. It doesn't matter which one's first. Okay. Okay. Okay, so what you have here is the correlation coefficient. You want to look at the off diagonal. For example, here, the first element, 1, 1. Okay, that's how you read that matrix, right? The element 1, 1, 1, 2, 2, 1, 2, 2. So 1, 1 as an index here means that the correlation coefficient between variable 1 with variable 1 is 1. So your diagonal here will always be 1. So the off diagonal will tell you the relationship of variable 1 with variable 2, and this one's the relationship between variable 2 and variable 1. They'll always be the same. Okay, so it's very weak. It means here you can now come back and tell your boss that, hey, the correlation coefficient, it's not that strong. So that's it for this video. We've only just covered the basics of what you can do with NumPy, but I hope with the examples that we have discussed, you see how powerful NumPy is as part of a data scientist toolkit in calculations and even performing basic statistical analysis. You have to remember how efficient NumPy arrays are in terms of performing this operation, the element-wise operations. And in another video where I will be discussing the more advanced concept for NumPy, we will be seeing how efficient it is in performing matrix operations. But for now, this will do for our basic understanding of NumPy. Hope you found the video quite helpful, and I'll see you in the next one.